So dear friends, welcome again. In our last session, we have some overview about the 3D printing, and I tried to explain some of the things about the fused filament fabrication, which we call as the material extrusion based 3D printing. And we have seen some small case studies how to make our in-house filament, and parallelly we see one case study for the dry cell. Now extension to that, we will be seeing some of the part for the 4D application where the exotic structure has some meaning. So for that, as you can see in your slide right now, what I have done is I have prepared some two color layers. One is the blue color, another is the green color. Basically what I am interested is I am interested in printing the layers. One is the non-conducting, another is conducting. So whatever we are seeing the blue color layer, this is basically the non-conducting. Just imagine I have the filament with me and I have printed the ABS layer. Then the green color is basically ABS reinforced with some, let us say, metal powder or the graphene part, and that is giving me the green color. Then again the insulating ABS, then again the conducting graphene. So multi layers, alternatively conducting and non-conducting, has been prepared. Now what I am trying to do is I am using a simple principle of physics. So we are allowing the current to move in a particular direction. So if the, let us say, the current is flowing from left to right, there will be formation of north and south, and similarly there will be north and south downwards. So this north and south will attract each other. So this is basically the effect resulting into the compression. Now if I just change the direction of the current, there will be south and south, so there will be repulsion. So basically this is a transducer which converts one form of energy into the another. So the idea is to develop a product which is like a transducer using a 3D printing. So again the process is quite simple. What I have to do is I have to apply alternative conducting and non-conducting layer, and then putting the value of the current into it, so that the alternatively north south are formed, which leads to the attraction, and if I put the south there will be a repulsion, right. So you can see this in this video in front of you. I believe that all of you can see this video. So this is the actual part as a transducer that has been prepared, and what I am doing is with the use of the basic physics principle, I am making the part to compress, I am making the part to expand, right. So this is the another video you can see in a simple way, you know, right. So continuing with this, now actual application of this type of part. Now in front of our screen there is a process called ultrasonic machining. All of us are as a manufacturing person are quite familiar with this. Here I am using a transducer. If I buy this transducer, this may be something around 20 US dollar, but if I make the same transducer with the technique just now we have seen, this will be less than 200 rupees, right. So there is significant cost saving and we can develop our in-house product. The idea is again to convert the electrical energy into mechanical vibration, and just by changing the direction of the flow of the current and changing the magnetic field, we are able to make a part which can compress and can expand. Now as a basic principle, through this setup there is a amplification, and finally there is a tool which moves with the ultrasonic vibration frequency, and there is a gap between the tool and the workpiece, and the slurry particles are allowed to move between the tool and the workpiece. So this all we understand is a typical ultrasonic machining process, and this has been used since 50s in a big way. Now one of the problem with this type of process is the tool weight over here. You see, as per the nomenclature available, this tool is basically a overhanging type situation, and I have to compromise with the height or the length or the weight of the tool, which will be basically responsible for the high tool wear or customized tool wear, right. If I want to have a more MRR, more material removal rate, and customized tool life, basically I have to make this tool from a material which is of lightweight. So what actually we did is we made a tool with a polymer which may be nylon 6 or ABS with a reinforcement of alumina and silicon carbide, and we printed this on a printer using 3D printing. And the selection of the abrasive was like in the first zone there is a coarse particle, then in the second zone there are fine particle, then in the third zone further fine particles are there. Now just imagine, now the as the tool will be vibrating, first the coarse particle, let us say, which are of AFS number 400, they get in touch with the workpiece. Then the AFS 600, they get touch with the workpiece. Then AFS 800, they get touch in the workpiece. So this is basically leading to the broaching of the tool or the hole generated inside. So this is basically a hybridization of the process in which drilling, ultrasonic drilling, as well as the broaching is going on, and that is only possible through 3D printing. So this is one of the patent that our lab is having for the development of the hybrid processes, right? And we can think of this type of hybridization in a big way. So specifically coming to the 3D printing part, what you will observe in most of the commercial 3D printer, we have the nozzle which is like a circular form, as you can see in this figure. So once there is a layer deposition or there is a solidification, it looks like a ellipse, right? So if the solidification is like that, the layer deposition will be like this. You can see over here there are air gaps, right? We call it as a Baru effect. There is a established effect by the material. If even I have a circular nozzle and the wire was initial circular, that was a feedstock filament, once it comes out, it leads to the formation of the elliptical part, and there is a lot of air gap that we see over here. Now to solve this problem, I have to go for the post processing, which basically adds the cost. This is one of the limitation of my 3D printing processes. So what we have done as a novel part into it is we made the nozzle which is like a convex shape, and once there will be solidification, this part which is this contour that we are observing, after swelling because of the Baru effect, it becomes a triangle. So all the layers were of the triangular shape, and then the second layers were inverted, put like a inverted triangle. So here I am getting a better packing factor. See, we got this idea from the color television. In 80s, there was a one local brand of color TV, and I believe that its name was Texla in this region. And after some years, the Sony came up with a technology, and they call it as a Trintron technology. So what they have done with the conventional way of illuminating the screen was, whenever they strike through the electron guns on a silver screen, they basically optimize the speed of impingement, then the standoff distance, then the angle, in such a way that the pixel that we are getting on the screen, those were not circular but the triangulars. And the name of technology they have put like a Trintron technology. So getting the motivation from there, we use these triangular shape layer by layer deposition in place of the elliptical shape layer by layer deposition. So this basically improves my packing factor, and I am getting a better finish. I have seen some of the printers in which people have parallelly employed 10 or more nozzles. Like taking another example, suppose if one nozzle is like this, which is giving me a circular shape, and at the end the deposited material is like a ellipse, then what we can think of, the second is like this star shape, and after swelling it is giving me some shape like this. So the packing factor is improved as compared to this. So we can think of this type of arrangement in a parallel system, and I can basically improve the productivity. Now, how much will be the swelling? What will be the Baru effect? For every material, I have to correlate it with the MFI of that material, and accordingly, I can customize my nozzle shape, and I can customize the extrudate that is coming from the packing factor viewpoint. Right. Now we'll have one case study for this type of sustainable innovative material and structures. Now this is one of the project that we covered under the Shri scheme of DST. Now whatever you are seeing in your screen, this is basically a heritage structure. In our country, as per the CPWD guidelines, the heritage structures are like grade 1, grade 2, grade 3. Like typically for the grade 1 structure, like the Taj Mahal, there is a protocol by the government, by the CPWD guidelines, like to work something in grade 1 structure, I need a lot of permission and I have to show a proof of concept. So normally the grade 1 structure in our country, they are managed by the Archaeological Survey of India. Then there are grade 2 structures which are again managed by the government, maybe central government or the state government. Again there is a protocol. Then there is a grade 3 structure which is normally a private property, but of course it is also having a heritage value. So what we normally do is we give a proof of concept in grade 3, then in grade 2, and then in grade 1 structure. Now we want to use this innovative technology of 3D printing into these type of these structures. Now what is the problem? You just see over here. Let us say this is a wall of the heritage structure, and this side of the wall is accessible to me and this side of the wall is not accessible to me, and suppose there is a crack in this wall, right? Now one of these commercial solution that is available with us is using a epoxy material. There is a multinational company, Hilti, which is quite familiar with our civil people. They are using lot of solution of this company, which is basically putting some epoxy into the crack, right? Now if the crack is like a parallel as you see over here, there is no problem, right? Now this is the second case when the entry side of the crack is large, but on the other side, it is small, right? Again there will be no problem. But there is a third case when the entry is small, but on the other side, which is not accessible to me, I am having a crack which may be propagated upward or downward direction. So here the epoxy may not fill. So the crack propagation, may not be controlled in a better way. Now to solve this type of problem, I need a smart 4D exotic structure which can be really useful for filling this type of material. So what I need to know is what is the size of the crack. So I need to know the volume. Then I need to have some smart material, maybe through exotic structure, which once entered into the cavity, it is small in size. So once it is entered, I give some stimulus, it takes the shape of the cavity. We got this idea from the Mruti workshop. Whenever you go to some of the workshops for the routine maintenance of your vehicle, so what they do actually, they put your car or any vehicle you are having on a lift, and they basically they put the lift up, and the operator basically unscrew all the tires, right? So for that screwing and unscrewing purpose, they are having a pneumatic gun, and through that pneumatic gun basically they put the supply of air either in the clockwise direction or the counterclockwise direction, through which you can screw or unscrew the nut. So taking the idea from there, can I think of some material which once I have to add, it becomes smaller in size. So once it is inside the cavity, I give some stimulus and it takes the shape of the cavity. So that is the idea of 4D and the use of the exotic structure in this type of application. So if we develop this type of material, and this lead to smart assembly and disassembly of this type of the part. Some of the structures, heritage structures, over which the use of exotic structure can be really useful. As you can see, there are a lot of all British period canals. This particular picture that you are seeing, this is called Bathinda Branch Canal. There are around 150 plus bridges of this type, for which we have to make these type of smart structures. Here you see, normally these all structures are good for the compressive loading, right? But suppose there is a in any case the compressive loading, because of the movement of the earth is not there, the whole structure can shatter, right? Downstairs you can see, this is another heritage structure which was built by a Mughal general. His name was Lashkari Khan. This was something in 1590s. This particular structure was built, and this is on Amritsar Delhi National Highway near the town called Doraha. So this is known to a cement structure, but we have to preserve it using a smart materials, and we cannot use the foreign material like epoxy to have a smart structure refilling in this type of case. So there we need a smart exotic structure, and we need to make a digital twin of these type of structures, right? So to give a proof of concept, basically what we did is we use three different materials. One is ABS, another is PLA, and another is HIPS. Now, how this will be important? Just imagine there is a curve structure like this. Now, on this is a single composite, right? On the top, it is under the tensile loading, and on this, it is under the compressive loading, and there is a neutral axis also. Now, if the whole material is a single composite, it will definitely going to fail. The better solution can be if I put some material which is having a better compressive property, that I put downside, and better tensile property that I put on the top side, and then I assemble. So that is the idea of using these three materials over here. So we used HIPS, that is high impact polystyrene, ABS and PLA, and they have a significant difference in their melt flow index. You can see the observed value here is 7.5 with a standard deviation and standard error that has been shown in the tabular form in front of your screen. Then for ABS it was 8.7, for PLA it was 13.52. So you can see there is significant difference in flow properties. So that means the thin section that I am interested to make is how significantly different for these three polymers. Then you can see there is a difference in their Young modulus like 112, 175, 47. Similarly, other properties like yield stress, glass transition, peak load, peak strength, elongation, there is a significant difference. The idea is just to give a proof of concept that by selecting three different material for this type of structure can be a useful solution through 3D printing, right? So what we did is we use some standard settings over a open source 3D printer using the fused filament fabrication only, and we fix some of the parameter like nozzle dia of the filament, layer height, number of the peripheral layers on the top and bottom, infill pattern, their parameter speed, travel speed. What we varied was in some of the combination we put ABS first, PLA in the middle, and HIPS in the last. In another case, PLA first, HIPS in the middle, ABS in the last. Then in another case, HIPS first, ABS middle, PLA in the last. Right, so we call it as APH, PHA, HAP. Basically, this is representing a combination of the material. Which material is printed first, which material is printed second, and then followed by the third layer. And we can change the infill percentage, then printing speed. You can see over here, this is the standard ASTM D638 tensile coupon. Here you can see the top layer is of PLA, here the top layer is of ABS, here the top layer is of HIPS. Load deflection diagram, we can call it as a stress strain curve also. When I use a single material, means this type of multi-material or the functionally graded has not been printed, but a single material like PLA, ABS and HIPS has been printed. Now what happens when we use this type of the hybrid material? Before going to actual mechanical property, we try to see their variation in the thermal properties, like I have explained in my previous lecture that we are interested in their thermal analysis, like which material is stable, which is not. You can see in this case for the ABS, which is represented by a black line curve. So in the heating cycle as well as in the cooling cycle, the energy absorbed and released is almost in the same range. Whereas if I go for the HIPS, you can see there is a variation in the energy absorbed, and specifically for the PLA there is a large deviation. That means PLA is relatively less stable thermally as compared to other two. So to put the point that their mechanical properties are different, their thermal properties are different, and what happens when I am using this type of the hybrid structure. Now this is a typical stress strain curve or the load deflection diagram that I observed for the using the different combination based on some design of experiment, and you can see the different curves. Area under the particular curve is representing the modulus of toughness. Basically it represent how much impact load under certain impact condition that material can withstand, right? So we try to correlate it with its morphological property. Like you can see in this first case, at 30x magnification, the ABS was printed and we can clearly see the layer by layer printing of material. Similarly, that layer by layer fabrication in case of PLA, layer by layer fabrication in case of HIPS was also observed. Now, once we do this with a multi-material, like you can see case 1, I have ABS printed first, followed by PLA. You can see some globule formation is observed. That means once I will print the material like this, in which the PLA will be in the center and HIPS will be in the top, there will be some side flow of the material. Whereas if I put PLA first, HIPS later, there is no side flow. Now if I just compare the curve 1 and 4 in my previous case, you can see the area under the curve for the 1 is like this, and for the 4 it is much more. So definitely the mechanical property that will be better in case of the fourth case, which is counter verified from the morphological analysis. So what I want to convey from here is, whenever using these type of material for some sensing or the exactic application, I must understand which material I have to print first and which material I have to print later, and that can be optimized, and I can think of different mechanical properties. I can customize those type of mechanical properties. We can also think of a customization of the thermal properties based upon the reinforcement. So I think this is a new dimension in the development of the smart materials. I hope you enjoyed this. In our next session, we will see the another application of these type of the innovative materials printed by 3D. Thank you very much.